Alright, so today we're going to do a multi-range simple current meter. Basically, all we have here is a simple current meter from the previous video where we have a panel meter that has and we know the full scale deflection current, or the I meter, and we need to extend the range to use our panel meter to measure currents larger than the full scale deflection current for the panel meter alone. And so basically, in a multi-range one, we're essentially just doing the same circuit 3 times. So we have range 1, and we have a selector switch. And so when we're on range 1, when we have range 1 selected, the range 2 shunt resistor and the range 3 shunt resistor are not part of the circuit. They're just sitting there. And so I could use my selector switch to select range 2, and then I can use my selector switch to select range 3. So really I'm only using one range at a time. I'm using my selector switch. I'm essentially doing a simple current meter 3 times for different range currents. Alright, so let's pick some range currents. And so my DMM, or a typical DMM, let's just say I of range 1 will be 200, let's call that range 1, 200 milliamps. I range 2, actually, let's do this again. So I'm looking at my DMM, and it goes 2 milliamps, 20 milliamps, and 200 milliamps. And I could do the 20 milliamp or the 20 amp range as well. But for today, I'm just going to stick with my 3 range as displayed in my schematic. Alright, so there's the 3 ranges that I'm going to choose. Alright, and so now I have to design my meter to work with these range currents. Now, on your meter, you're going to need to measure the characteristics, so you know the full scale deflection current. I'm going to use a 1 milliamp just as a spec, and then I'm going to use my internal winding resistance of the panel meter, the analog meter, 1 kilo ohms. Alright, now let's see. So now we have to decide what we're going to do. So basically what this current is, the full scale deflection current. Alright, so to move the needle to the end of the screen or the end of the display, like this one, alright, so the little red needle is all the way to the end at full scale deflection. Basically the spec is telling us that if we pass 1 milliamp through this thing, so 1 milliamp of I meter is going to cause full scale deflection. So we're going to calculate it at full scale deflection. Alright, and so on range 1, we're saying is we need to figure out what RS is. Alright, RS1 we'll call it. Alright, so what I'm saying here is range 1 is 2 milliamps going in and 2 milliamps coming out of the entire circuit. I know that I meter is only 1 milliamp at full scale deflection, so the R1 is going to be my shunt resistor for range 1. So I need to determine how much current, how much current do I need to shunt away from the meter or reroute away from the panel meter, and how much, and then therefore how much resistance is that going to take. So I determined in the previous one, I think this is exactly the same. So range 1 is exactly the same as before. So I determined that V meter was just going to be Ohm's law of I meter times R meter, and V meter was, so we got 1 milliamp. Okay, so you're going to want to use the measurements that you've determined for your meter if you want to make accurate predictions, that is. But just on paper, we're going to just work with these numbers, and to do measurements we have to verify. So V meter turns out for this meter was 1 volt, and it'll always be 1 volt for this meter with these characteristics. Alright, so basically in my parallel network here, I've got R meter in parallel with R1. Okay, and so that entire network sees 1 volt at full scale deflection. Alright, and then I figured out from before, so I shunt, and we'll just say shunt 1 because we have multiple stages here, or multiple ranges. I shunt 1 is going to be I range 1 minus I meter, which is constant. Alright, 2 milliamps minus 1 milliamp, so IS1 equals 1 milliamp. Okay, and then now RS1 equals V meter over IS1. Okay, V meter was 1 volt over 1 milliamp. Okay, so we're right back to alright, let's just bring in the old calculator just to see it happen. Okay, let's look at it. 1 divided by 1 milli. Okay, so we're right back to 1,000. Alright, let's write it in engineering notation. 1 kiloohm. Alright, so there's 1. Excellent. Alright, now we do have also that range resistance. So R, you could think of range resistance as your total resistance. R of range 1 equals, we'll just do the parallel formula just to show it. Rm 1 over Rs1 Alright, and I see that they're equal numbers, so I already know that it's going to be 500 ohms. Two equal values in parallel, two equal resistances in parallel are just going to be half of whichever they are, or of whatever the value. Okay, so there you go. So now we could build range 1, and we can run 2 milliamps through it and measure full scale deflection as 2 milliamps passes through the entire meter that we've just constructed. Alright, so let's quickly do range 2. Alright, so some of this is going to be the same, so V meter is going to be the same. This formula essentially is the same, but let's go over here and I'll say IS2. Alright, so now I've got that's moved here, so now my current is flowing through this resistor. Right, so now I'm shunting at that node. Alright, and IS2 is going to be there. So I range, whoops, let's get my colors consistent here. I range 2 minus I meter. Okay. Let's just rewrite the same thing again. 20 milliamps minus 1 milliamp. Okay, IS2 equals 19 milliamps. Alright, so now I can figure out R2 or RS2. I'll be consistent. So R2 is the shunt resistor for range 2, and that's going to be V meter, which is still the same, over IS2, so RS2, shunt resistor is going to be 1 volt over 19 milliamps, so RS2 is going to equal 1 divided by 19 milliamps. Alright, so I'm getting for this one a 52.63 ohms. Okay. Alright, well that's really nice. So there's that one. Alright. And the range resistance, we probably had to do that too, because we want to have some idea what our loading effect is going to be. It's going to be around 50 ohms because I have 1,000 ohms of the meter in parallel now with my 52.63 ohms. So let's just show that. 1 over 1k ohms plus, let's get my formula right. 1 over Rm plus 1 over Rs2. Okay, so R range 1 over 1k plus 1 over 52.63. Okay, let's just pull that up, type it in just like we see it. 1 divided by 1k plus 1 divided by, I'll just bring my minimally rounded number in and close parentheses. Make sure it all ended up in the right spot. Oh man, look, 50 ohms on the dot. So R range equals 50 ohms, and that's range 2. Alright, very good. So now one more range to do and then we're done. So the steps are the same. This time that current is being shunted here, so I should have showed this for the other one. Now we're all the way up to 200 milliamps. 200 milliamps. We've still got only 1 milliamp going through the meter, so that means that 199 milliamps need to be shunted away. Alright, so if I may be so bold, RS3, 1 volt over 199 milliamps. Alright, so let's just see what that comes out to be. 1 divided by 199, whoa, e to the negative third, is about 5 ohms, so 5.025 ohms. Alright. Okay, so now our range resistance is going to be 5 ohms in parallel with 1k ohm. I'm going to say about 5 ohms. I'm going to go ahead and just calculate this one. So our range 3 is going to be, let's do the shorthand now, R meter in parallel with RS3. Okay. Alright, so now let's just do that. R range 3 equals, let's get the calculator in, Okay, so I've got 1 divided by, I'll go ahead and do it the standard way, 1 divided by 1K still, so our meter hasn't changed, and that should be 1 divided by 1K plus 1 divided by our minimally rounded number up here, and close parentheses, and here we go. So 5 ohms. 5 ohms. Okay, so 5 ohms is how much meter loading I would have in this circuit. So I found my 3 resistances. I found my 3 range resistances. Now I can measure with my ohm meter. Let's get in here with a different color here. So I can measure with my ohm meter. So if I had my ohm meter here, okay, so whichever range I have selected, I can put my ohm meter right on the input leads of my designed simple meter, and I should be able to measure fairly accurately the range resistance. So that's my 5 ohms for range 3, my 50 ohms for range 2, my 500 ohms for range 3. Alright, so that tells you, well, I've got it hooked up properly and everything's good. So now at each, for measuring this, these are very small resistances, so to measure current directly, you're definitely going to run into some current meter loading problems with your DMM, and I'm going to hopefully get another video soon of the measurement process. So what I find is that because the resistances are so low, current meter measurements are kind of impractical unless you know the range resistance for your DMM and you can account for that. What you can measure accurately is your full scale deflection voltage, which is 1 volt. So basically you set up that 1 volt, and you should, well, actually you adjust for full scale deflection, and you should measure about 1 volt if everything is built properly and accurately. So these predictions should be good, but to prove it, we can go into the lab and actually take measurements. So this is the basic circuit. We've got essentially 3 simple current meters in one, designed to extend the range or the measurement capabilities of a simple, or of a D'Argenval analog panel meter, and so we can extend that range to whatever we want, which is kind of nice. You're going to want to know the range resistance and of course the individual shunt resistors. So go into the lab and try to build this thing and measure it and see if your predictions are accurate. Alright, that's it for now.